So good evening, folks. So today we will be discussing a new design. We will be designing a messenger. So basically, the requirements I've already written on the screen. On the basic level, we will be designing the messenger on for the WhatsApp scale, which is basically 2 billion monthly active users. So yeah, over to you, Kaushik.
Okay. Okay, so WhatsApp scale is like 100 billion messages per day. I see. And you have written here message permanent storage. So WhatsApp doesn't store message permanently. So do you want to store it permanently forever?
Yes.
Okay. And also there is multi-device support. What does it mean? I mean, I as a user can log in from mobile and from desktop. Is it something like that?
Yeah.
Okay. Okay, it's a global app. Okay. End user app, end user app. Okay, so one-on-one special case of group chat. Uh, one-on-one special case of, so it means that any person, let's say if I chat with you, that's kind of a group chat only, just that there are two participants.
Yes.
Okay. So you also want to show online status of messenger, and also one person can have 1,000 connections. So do we need to concern about connections, or you can just assume that the connections are there, let's say?
Yeah. I mean, this number is not really important here. So the online status of Messenger, I mean, how is it different from WhatsApp? Is basically WhatsApp doesn't show you all the people who are online. So you need to basically go to the chat and then you can see who is online.
Okay.
Whereas on Messenger, you actually see a list of people who are online. So it's basically a list there. So
So
even
you
if
see,
you are not
you
chatting with anyone,
You see only online users? That's what you're saying, or offline also?
not offline, yeah, let's ignore the offline.
Okay, okay, I see. Makes sense. Okay, for non-functional requirements, it has to be scalable, yes, and latency online users less than 500 millisecond. Okay, is this just a random figure, 500 millisecond, or I mean, or just you want to mean that it has to be very low latency system?
So 500 milliseconds is actually still a large number. So I mean, most of the companies target 200 milliseconds for a normal REST call. So I think let's keep it. I would say 100 milliseconds.
Okay, okay. Fine, that's a very tight time though. Okay. And also you need a high throughput system, availability, message ordering. Yeah, message ordering is important. Eventual consistency. Uh, okay, so in the context of multiple devices, it is eventually consistent, is it?
Yeah.
Okay. And encryption, security, and data durability for long term. Is encryption and security we are concerned about right now, or it's just good to have here?
Good to have. I mean, not really that important for the scope of our discussion.
Okay. No, ideally, it's a very important feature for this messenger application anyway. I see. And data durability. I think we discussed data durability, right? That we need message permanent storage. Okay.
Yeah.
I see. I think let's start very small here. I mean, are there any other thing that you would like to add? You have already added almost all the things.
Yeah,
Uh,
we can.
okay. Uh, I see. So I think there are two things very important here. One is definitely this low latency that we're concerned about here, and another is this data durability. So we need to make sure that we have all the messages saved correctly for long term. And we also need to make sure that the latency of the message application is very low, since it's a very, and also it's a very high throughput system. I see. And since it's a global system, availability by default has to be there anyway. Yeah. Uh, okay. I think we are not going ahead with any estimation right now, since it's already a big system, right? So we know that it's a very global system. So let's actually start with very small design first, and let's see actually how to actually scale it. So let's say that this is the user A, and also uh, and there is this user B. User B. So now if user A needs to send a message to user B, it's not like a it's not like directly connected. These mobiles are directly connected to each other. So we need some server will be definitely there, right? Say some application server is going to be there through which the messages are going to send. So let's call it chat server, right? So let's say user one wants to send a message to user B. So user A most likely in this small application calls an API, right? So some API like maybe API some version and say message, and this is kind of, let's say, post message. So I'm not much concerned about API signature here. If required, we'll discuss later on. But just for understanding here, so user actually sends a message to the chat server, and now user B has to fetch the message. So since it's kind of a real-time application you want to develop, user B, has an option to actually poll the chat server. So what are the different options to actually get the message? So user B can connect periodically to the chat server, let's say every 5 minutes, and get the message. Or to make it more real time, it can poll, let's say every 2 minutes, or every 1 minute, or every 30 seconds, something like that, right? So within a feasible interval, it can actually fetch the message from the chat server, and a bunch of messages actually come to user B. So API, let's say version 1, and messages. So it's an array of message, and it's a get, right? So it's like a polling method that we are actually using here, right? And the polling happens at a favorable time frame. Let's say maybe every 5 seconds or so, if that actually serves our user better, right? So for a small scale user, uh, uh, just calling this API to fetch the array of messages or array of those those objects should be good enough, right? So now the flow is very simple here. So here, since persistence is also involved here, we store this basically message to some database here. So for now, I'm choosing relational DB just for the sake of simplicity. We might discuss later what could be the real choice of the DB here. But for this small scale application, our chat server can actually store data to relational DB. Now this is at a very high level. Now at a high level also, we need to know what kind of data we are going to store here. So we are actually going to store messages, right? So just to give you some glimpse of the data that we are actually going to store here. One is messages. Or before messages, we need to actually store, users. And also spoke about, okay, this is for 1:1 basically. So user A and user B both are in this table, and they can send each other some messages, right? And also, I think we are supporting group chat, right? So we'll be a separate entity to actually store group level data. It's a group ID, group level, maybe group level settings, group name, and different other metadata of the group, and maybe group chats. Sorry, what do you call it? Group members. So this group member is a table which essentially stores, that for a particular group who are the members. So there will be one single row for each member in a group. So all these data in now are relational, considering that it's a very small scale system, right? Now we'll actually try to slowly scale up the system. So you have any thoughts till now?
Yeah, I think we are good. We can scale this.
Okay, so cool. So now since okay, so there are a couple of requirements regarding scale here. So one of the things that I see is that it has to be globally available, right? It has to also do multi-device support. So we'll come to them one by one. Okay. Okay. Now let's say if the user increases. Let's say if the user increases 10 times, or say 100 times maybe. then one of the easier ways to actually scale it is that at the application side that we actually increase the number of application servers, right? So you might end up having multiple actually chat servers here. This is assuming that our DB is actually still able to handle the load, right? So we add few chat servers here, and now this users can connect to any chat server. Let's say user A actually connects to chat server 1, and user B still now ports chat server, and this relational DB is actually can be accessed by each and every one of these chat servers, right? So all of them can actually talk to this chat server, and the APIs directly serve data from this DB to the user. So any chat server can fetch that, can retrieve, or can actually insert data to this relational DB, and it still works fine to up to some level of scaling. Now, the next bottleneck that will come in actually scaling is our DB cluster actually scaling. So since let's say we have 100 times more members, let's say we have now 100,000 members. Previously we had probably 1,000 members. Right now we have probably 100,000 members. So you now want to actually scale this relational DB also. So this is just a step-by-step scaling that we are actually talking about here, right? So one of the ways to scale the relational DB is probably vertical scaling. You just want to add more powerful machine, but that will have also certain limitations. Up to some point in time, that scaling won't work, or it will be very expensive to do, right? Or you will actually your cost will go through the roof. So what might end up happening is that we might want to some level, we might want to enable a level of partitioning to our relational DB here, right? So that data can be evenly distributed between these two relational DB, right? So so these relational DB here, they are kind of partition, and for now let's assume that they handle 50% of the data each, right? And let's say that for now, I mean there might be different partitioning strategies, but at a high level we have just enabled partitions, and our DB cluster can actually serve this load, right? Now, since it's a global app, so I'm just assuming that it's the app is actually available everywhere, right? And okay, before I go ahead, do you have any questions here, or you want to add anything here?
No, I think we are good so far. I mean, we'll have to look at the latency as well.
Yeah.
But yeah.
Yeah, so I think this gradual scale up actually helps you as you get actually linear number of increase or linear increase in number of users maybe, right? But it probably won't help you when it's actually a global app or huge app. So let's now see some scenarios when it's probably a global app, right? It's a very huge app. So now in real WhatsApp kind of system, what happens is that uh, so these chat servers are distributed globally. So let's assume for now that this chat server is in Europe, and this chat server is in let's say South Asia. They definitely have their own redundancies in every region, but for now, let's assume that these are different chat servers, and we are now some user A from one region can now send or receive message from some user B in another region, right? So here there are many loopholes, there are many problems here actually. First of all, most likely what is not going to work is this poll mechanism is not going to work because it's a huge scale, and sending 100 billion messages a day is not an easy thing. So if you want to keep on polling the system, your system won't be efficient. How many times you can actually poll the system? The system will be loaded completely, right? Because of so many HTTP handshake and HTTP connection creation, and those kind of things are costly in nature. So probably the first thing that is not going to work is our poll mechanism. So you need to find a better mechanism so that these messages can be transferred both ways. Now, since it's a both way, one of the option is to probably use WebSocket. It's a duplex connection. I think we discussed it in our previous videos also. So what will happen is that user A, any user basically, user A, user B, or whoever the users are, when they log into the app, they first make a WebSocket connection to their respective regional servers. So user A can make a connection, a WebSocket connection to one of their chat servers in the Europe zone, right? So instead of using this API, now, it might actually just open a WebSocket connection, to this particular server, EU server, right? In a similar way, this user B can make a connection, uh, to server underscore, let's say, NA. So there will be proper address and stuff like that. But yeah, so these are nothing but at a high level the server address, which will probably eventually boil down into multiple DNS servers in the same region. So any user will be connected to just one of the particular hosts, in that region. So now we have this chat server EU getting a lot of connections or maintaining persistent connections to a lot of users, and chat server N also and chat server S also maintaining connections to a lot of their respective users, right? Now there should be some way so that the messages can be actually transferred between one chat server to another chat server, right? So one of the ways might be just that each and every chat server knows about other chat servers. So chat server EU knows that chat server SA is there. I mean there are multiple hosts in South Asia, and there are multiple hosts in North America. So there should be some way so that chat servers can just basically maintain some level of, let's say, gRPC connection, and can send message from them to the other chat servers, right? So that they can actually talk directly. So now what will happen is that, let's say, whenever user A wants to send a message, it sends the message to chat server Europe. Now chat server Europe has some way to figure out that, hey, this message is for some user in the North America region. Who is the host, right? Or who is the, basically which chat server, which region I should actually send this message to. And once it identifies that what is the chat server where the message should go, it just sends the message through that connection to that chat server, right? And it's now the responsibility of chat server, let's say in our example, North America, to deliver that message to the connected user B, right? So now this information has to come from somewhere. It don't come from the thin air, right? So what I'm thinking is this, that there should be some level of registry somewhere, right, which will actually say that which maybe which user is actually connected to which chat server, right? That level of information at least we can manage. So that seems like more of like a very key value kind of information, right? So this is like we can probably call it chat registry, chat registry, right? So essentially what we manage here is that we manage user, let's say user, it's a key value map. It maps to say user to, let's say, host and region. Basically some metadata, which identifies which region, which host the user is actually connected to, particularly in what region, or maybe some address, internal address or something like that, right? But at a high level, this is kind of that map. So now user A sends a message to chat server EU. EU looks for the destination. The destination is user B. So now chat server just talks to this chat registry. Hey, for this user B, who is the connected host, or which host in which region B is actually connected? Give me this data. So now it actually responds back saying that, hey, it is actually connected to North America in our example. So now chat server EU can actually directly talk to North America to send the message that, hey, I have a message for user A who is connected to you. I have a message for user A, deliver it to him. Now chat server NA has to figure out some way so that it can deliver this message to user B. So at a high level, it might happen that chat server NA knows, say user to, connection object mapping, right? So this is a very low level details that is available to every chat server. So every time some user is connected to some chat server, they basically register this information inside themselves through some library, internal libraries, that hey, this user is connected to me, and this is the connection object, and this is the WebSocket level of connection. So now what happens? User sends a message to chat server EU. Chat server EU, let's say, stores the message to the relational DB, and then chat server EU talks to the chat registry to figure out, I have a message for user B, which host, in which region should I send this message to? So it actually gives some internal address details and internal address metadata, using which chat server EU can directly talk to chat server NA, give this message to chat server NA. And now chat server NA, once it gets the message, it knows which connection object belongs to this particular user B. If the user B is online, it just delivers the message to user B through this WebSocket connection. Right. So that's kind of the high level flow that happens here. So any questions or anything you want to add here?
You mentioned that, if the user B is online, then it basically delivers the message. So how does it know, that user B is online? So what information exactly basically, retrieving from the server?
Yeah. So there has to be some level of ping mechanism from each of the users to these chat servers, which actually tells that, hey, I'm alive. Let's say any user can send a ping every 5 seconds or a heartbeat every 5 seconds, saying the chat server that, hey, I am alive. If there is, let's say, so when it is alive, this is alive when the app is actually open, the user is just integrating with the app, irrespective of whether he is actually chatting or she is actually chatting or not. We might just scroll up and down or see someone's profile picture. So at that point, you don't send any message, right? So at that point, every 5 seconds, the user any user can send a message, send a heartbeat that, hey, I'm alive. And apart from that, if you send any message, that's by default, it means that the user is alive, right? So this liveness information can be gathered from either from this heartbeat, which will be there if there is, let's say, no message sending, or if there is any message you are sending, then you can piggyback this information into this message to the server that, hey, this is also my liveness information that I'm also alive. So that heartbeat mechanism has to be there, right? And I think that heartbeat mechanism has to be captured somewhere in, we should actually call it, something like, let's say, presence server. Okay. So this presence server is solely responsible to actually keep track of the if the user is actually alive or not, that data basically. So what it can contain is that it can contain user, and it can contain the status. So status can be for now, so let's say online/offline, and along with some TTL. Let's say the TTL is 1 minute. So in the worst case, if the user is not alive, let's say somehow the app crashed or the app hanged up or something like that, right? The TTL will expire. And if you ask the presence server that if the user is available or not, right? You'll get no, it is not available. So what essentially the chat servers can do is that whenever the chat server has got a message from the chat server EU, chat server NA gets a message from chat server EU, either it can directly try to deliver it to user B, or it can just ask this presence server, hey, is user B online? If yes, then it can try to deliver the message. Otherwise, the message is not delivered, and it will be delivered later on when the user actually connects. Right. So this is kind of an optimization. So this presence server information can also be used to show the online offline status also. If you want to show the online status of the users, we can query the presence server with the connections, of, let's say, user A or user B. We can find who are online, and we can actually show them as an online, right? And before delivering a message, if we need to identify if the user is online, we can actually do this identification from here. Now, if you don't use this presence server while delivering this chat, it might happen that the chat server might think, depending on the business logic, the chat server might think that, okay, fine, it's probably the client has not received the message, so it keeps on retrying, right? 2-3 times or 4 times it retries, but the message still doesn't get delivered. So why to actually do that? Why to even keep on retrying multiple times when the client is actually offline, right? So that's why it's probably better to actually check the presence. If it is online, then only try to deliver the message. In the worst case, within this 1 minute TTL, it might happen that it's actually offline and some retry might happen. So it's kind of an optimization on top of that. Yeah. Yeah. Any other questions or any thoughts here?
Yeah, this part is good. You mentioned that there will be one gRPC connection between chat server, let's say EU and North America. So
Mhm.
let's say if I have thousand servers, in my whole network, then there will be 1,000 connections per box. So
Mhm.
one box will be basically connected to 1,000, boxes, right?
Yeah.
And these
Yeah.
are persistent connections.
Yes. So
Okay.
yeah, I mean that's a trade-off of this approach that you have to allocate uh, some connections, dedicated some connections to all these chat servers, right? But this comes at the advantage that you can directly deliver these messages to these servers. I mean, there might be another option. Another option could be, using something like some level of POPs kind of mechanism. Let's say we internally use some message queue here. This is called message queue, but let's call it a POPs mechanism, right? Irrespective of the technology. So what will happen is that there will be you can assume like there will be some topic, and every chat server will have their own topic. Basically, every chat server will have their own topic, and they will just subscribe to that topic. So when the chat server is actually deployed, internally it actually creates a topic also in this pops up. Okay, and now if chat server EU wants to publish some message, it just gives this pops up system that hey, this message is for chat server NA, you put it there, right? So the once it is put on to the topic, the chat server NA sees that okay, fine, there is some new message for me, it just consumes this message. So this technique can also work, but the point is that it now comes at a cost of adding another system here, adding another PubSub system here. So now you need to actually manage these PubSub systems. You need to also make sure that if the chat server is lost or is out of operation, that topic is also deleted. So it actually adds some level of what do you call it, maintenance operation here. And at the same time, it's kind of a new system altogether. So if your PubSub system goes for a toss for some reason, all of your chat communication will go down, right? Uh, so these are just two different options. Either you manage all these connections, right? Or you don't manage any connection, you go through PubSub. Ideally, both solution can work, but still I would probably vote for the first option, given that that's a low latency. That will also comply with the latency requirement. But with PubSub, there can be a little bit addition of latency. What do you think?
So we can actually do one more thing. So let's say let's assume that we have 1,000 servers in our whole system, and let's say we have 4 data centers. So
Mm-hmm.
what we can do is basically we can create one representative server for each data centers. So
Mm-hmm.
rather than the chat server in you connecting directly to a chat server in NA, it can actually connect it to the representative server of NA, and that
Mm-hmm.
representative server will basically then forward the request to the actual server. So that way, this representative server will actually be connected to only 250 servers. Whereas, I mean, in the other approach, basically, uh, every server was basically connected to 1,000 servers. So still, we have basically kind of divided, you know, by 4.
Got it.
So maybe some kind of approach, some basically something like that.
Yeah, that also works theoretically, but again, it also similar to PubSub, it also comes with its own bottleneck. That what if the representative server actually goes down, right? You need to make sure that there is enough redundancy for that also. I mean, if your chat server goes down, that's fine because I mean there will be repercussions of that definitely, but that's kind of a stateless, right? A new server will come up, it will broadcast its presence and everything. Everyone makes a connection. But once your representative server goes down, uh, again you lose your chat basically. Again you lose these connections, and someone has to again come up. So that reduces the number of connections definitely, but it's again another system to maintain, right?
But
But
representative server is basically, I mean, it's also stateless, right? I mean, if these are stateless, so since I mean, if we are maintaining the persistent connections, then technically they're not stateless. But yeah, we can, I mean, since these are not with the we can call it stateless. So basically, the representative service is actually server is actually very much like them. So I
yeah,
mean, if we to ensure availability, then maybe we
yeah.
can have
So
more than
yeah,
one.
just to rephrase it, maybe just that there is one more dependency added. That's it. That's what I'm just saying, right? If you add PubSub, it's again a dependency. If you add the representative server, it's again a dependency. That's it, right? So we optimize the number of connections, but at the cost of adding this dependency. So just in case it also goes out of operation, there has to be deployment pipeline or automatic failover so that that representative server also comes up very fast. Yeah. So I think all these are three different cases, and all of them can work if I mean it's ultimately in the end of the day we need to do experiments at a very high scale and load testing and see actually if what actually works best for us in reality, right? And what actually complies with our what do you call it, latency requirement. Yeah.
Yeah.
Okay. Yeah.
So relational database, I mean, this is something that we have completed talking about it, or do you want to talk about it later?
No, we want to talk about it to the relational database. So even though so we chose relational database first of all just for that low scale, but definitely with this scale that we are actually talking about of 100 billion messages per day, uh, our DBMS is not actually going to work, right? So essentially, if you see, we need some system where we need some database which are very write heavy, or which are optimized for write heavy operations. So there are few parameters which actually might impact your database choice here. So one is what is the nature of the operations. So the nature of the operations is mostly write heavy here, because whenever you read some chat, you read most recent data, mostly probably last 1 month of data also, unless and until you search something and go back a lot of point in time, go back a lot. But usually you read the recent data, but you write a lot. So any write intensive any database comfortable with write intensive workload is actually a good choice here. And also you want to make sure that you want to make sure that the data structure that is used by the database, right? That is also good enough. Let's say that there are many document oriented databases which eventually write a document, and then if you read it, it reads the whole document and modifies it for update case, and then it actually observes the data. So it's a lot of document internally read and write. So you want to avoid those kind of things also. So probably document database might not be a good choice here, given. So we don't want to probably use DocumentDB because of the update operations that happen there. You read the document, you write the document in memory, and then you submit the document to the DB again. So for our low latency use case, that might not fit the bill. But again, we always can actually go back to our load testing and can experiment with our DocumentDB before productionizing the system and see actually how it functions. But most likely that won't fit the bill. Also, we want to since it's a very globally available system, right, or global scale system, we don't want to manage the system unless and until something really screws up there. So we want a system which can automatically scale, right, which is automatically kind of fault tolerant. Yeah. And definitely we'll have our own alerts on the APIs of the DB, so that if the 95th percentile response time goes beyond certain limit, we can actually get the response and stuff. And I think these are the main parameters, right? So we essentially want something which is not a document DB, which is fault tolerant, which can automatically partition the data, and definitely which is like extremely write heavy system. So I think in this case, Cassandra fits the bill, right, for all the requirements. So we can essentially introduce systems like Cassandra, or even there is something called ScyllaDB also. I personally did not use ScyllaDB, so I cannot talk much about it, but I have heard that that's also a very good alternative to Cassandra. But yeah, let's stick to Cassandra for our use case now. So Cassandra, in our Cassandra ecosystem, it's a very write intensive system. Read is not very optimized because for read you need to go through multiple memory tables and then SS tables on disk and then Bloom filters to figure out if some data is there in SS table or not. And then on some disk file to actually find out if the data is actually there or not and whatnot. So the read might not be optimized there, but anyway, for our use case, write is very much optimized here, right? So so Cassandra can help us with this write intensive workload. So we need to just put proper partition key here. Now, if you see, you probably spoke about you told that it's a group chat kind of application, and one-on-one chat is nothing but one special use case of group chat. So eventually, I'm assuming that there will be something like group ID, right? So at a very first look, the partition key can be group ID. I'll talk about the pros and cons, but let me first write it down. The partition key can be group ID, and the sort or whatever clustering key. Clustering key can be the message ID. So our message ID is actually Snowflake ID, right? So I'll probably push the link of Snowflake. So it's a basically auto incrementing ID, which has some time component to it and some other extra component. But it's very good. It's a very good. It's a very suitable ID generation library and system for these kind of applications. So our message ordering, the requirement that we have here, the message ordering, right? Somewhere you wrote the requirement of message ordering here, right?
Yeah.
So yeah, the message ordering here. So the message ordering will also be addressed by the Snowflake ID, right? So okay, now coming back to our partition key, group ID can be our partition key, definitely. But the problem is that if some group is overactive, let's think of a use case where let's say we open the group for any number of users in future in some country, right? And you suddenly have unbound number of users coming to this group, and they send a lot of messages or attachments and whatnot, and ultimately the group basically explodes, right? So that partition which handles that particular group might uh, you know might need to actually face the fire. It actually becomes a hot partition in terms of write also, even probably in terms of read also. That actually becomes uh, you know what do you call it, very hot kind of partition, right? uh, so in that case, what can happen is that with group ID, you need some other component for the partition key. So one component that I can think of is let's say time bucket. So in short, what you will do is that whenever you are actually getting the messages are divided into particular time range. It's not a static time range; it's a dynamic time range only. We'll have formula to decide the time bucket. Uh, but from some start time to end time, all the messages that come that will actually go to this partition, to this specific partition for this group. And in a similar way, from the next time, last time timestamp of this group to some other timestamp, all the messages that come there will actually go to another partition belonging to the same group. So in this way, we don't have a single partition of the same group. We have multiple partitions. So even if the hot partition happens, it will happen for a very small time range kind of small time range kind of basically partition, even during read time, right? If it happens, right? So that time bucketing is important, but again, this time bucketing is kind of for our example, it's kind of an early optimization here. We need to actually see how our partitions are actually performing with just simple group ID. If it doesn't perform, then a futuristic thought process might be using some level of time logic there, which time bucket, so that the partitions can be much more optimized. So you have any thoughts here or any questions here?
I think this way we would have solved the problem of uh, huge data that is basically getting in a hot partition situation, but the huge reads and writes that we would be getting in a particular hot partition case, that problem is, I think, still not solved.
Yeah, I think this solves the problem of write partition because you have all the partitions, new partitions getting generated, right? For the
Mhm.
write, and the data is always append only. You're not you're not updating any data because Cassandra updates data in a different way than relational databases. So almost the write thing is solved here, but the read thing is definitely not solved here. So still you might have some partitions where a lot of reads are actually happening. Along with write, the system probably becomes very slow, right? So I mean, there can be one easy way to actually scale that read is like probably using caching here, right? Let's say that if we, is there any cache here? Okay, so let's say that, okay, for now, let's say that we add a level of caching here, right? So this is, to keep it simple, let's say that this cache automatically retrieves data from our data store, right? Sorry, it should be the opposite. So it retrieves data from our data store, and our application can actually query this cache to actually get the data to solve the read problem. So here there are two problems here. First of all, it's again a new system. So with our previous philosophy of keeping the system simple, managing the cache cluster and scaling, you need to scale the cache cluster also, right? So that management becomes a problem here. And another problem might be that the cache is not synced properly with the DB cluster. I mean, there are different ways to actually sync the cache with the DB. One is change data capture, or another is maybe I forgot the name of this caching strategy, but something like pushing the data from the DB cluster to the cache cluster every, let's say, few seconds, or every few to some, basically let's decide a threshold and put data from this Cassandra cluster to the cache cluster, right, of whatever data has been written. So that way you can actually sync the cache. But the problem is the management and scaling of this cluster here, of this cache cluster here. And in case, as a backup mechanism, if the data is not available in the cache, the chat server anyway have to come to the Cassandra cluster to actually look for the data, right? But I think management of the cache is kind of, if you can manage it, it's a good solution. But if you don't want to manage it, it's not a good solution. So that's a trade-off here. So what can be done here is that another mechanism that probably I can think of is that it might happen that in a group, right? Many people actually see the same message. It's very common use case that you or me actually see the same message. So when you are actually looking for some message, particular message, that you have searched for a message, you have gone to certain message ID, or you have scrolled up, right? So essentially, what is actually happening? You are scrolling up the messages, so we know which message IDs you are actually scrolling up, and etc. And we essentially try to fetch that message from the Cassandra cluster, and give the data back to the clients, right? So what we can do is that we can probably, instead of using the caching system here, we can probably use some kind of uh, let's say, okay, let's put this box here, some kind of worker system here, right? So what will happen is that if you are a user and you are actually trying to fetch a message from the Cassandra, so we spawn a very lightweight thread basically here, right? So this is actually our worker system. So uh, So we spawn a very lightweight thread to actually get the data from the Cassandra. And meanwhile, if many other users are also trying to get data of the same message ID, right, they can actually subscribe to this worker. So the requests they directly, all of their requests don't directly go to the Cassandra. Only the first user's request goes to the Cassandra. And while the lightweight thread actually checks for the message in the Cassandra, a lot of other requests come and they subscribe to this worker in this worker system basically. So this is our worker system, right? So this is kind of subscription system, right? So now what happens is that only one connection is there between this worker and the Cassandra, right? And it doesn't cache anything. Just that during the time, if a lot of concurrent request actually comes, all of them can subscribe to the worker, and the same worker can actually serve this message to all of them, or a range of message. Basically, we can try to extend the system to range of message also. So this system is beneficial if you have something like a group where some kind of announcements has happened. Let's say in a WhatsApp group, public group, or in a WhatsApp group of 1,000 people, someone writes a very important message, and all of the people are trying to now fetch the message. All of the clients are trying to fetch the message, right? So it's kind of a very likely concurrent scenario where all of them are trying to fetch the same message or same range of message, right? So then this worker system can actually come and can actually help here, right? So now again, it's a different system, but it's not like a caching system which you need to manage the state or which you need to replicate or something like that, right? It's just pure workers, right? If it crashes, another worker system comes into action. That's it. Nothing else happens. And maybe the client maybe retries and any request comes in case of worker failure, and the similar flow actually goes on, right? So that probably could be one scenario which could be handling your concurrent read scenarios, thus reducing your read load on any partition. So the hotness of the partition should be reduced. So any thoughts here?
So this read scenario is in case, I mean, the people are offline, right? If people are online, then I mean, we don't need to really, go to the database and read the message, right?
People are online, you don't need to read. Yeah. I mean, this could be either offline, or this could be either say searching something, right? I mean, you are basically searching for some message, some important message maybe. For online system, yeah, we are directly delivering the message, so we probably don't need that. Yeah.
So in the online as well, let's say if I have a group of 500 people, then the chat server in EU, let's say, so user A has written to a group, and then this chat server EU has to forward that message to 500 people. So in that case, then it will have to make 500 gRPC calls.
Yeah, I mean, in online use case, let's say in online use case, yeah. I mean, if I want to deliver a message of a group, then I mean, anyway, it's like the same thing, right? The users are connected individually to their chat servers, and each of the chat servers are connected to their own, to other chat servers through one single connection, right? I mean, EU and NA has only one connection, bidirectional connection, or whatever the connection is, right? So the only thing is that there has to be some level of group uh, group metadata system which will serve that who are the followers of this group or who are the members of this group, and then the chat server can deliver the message to all the concerned other chat servers, and those chat servers can send the message to the groups basically. That is for the online use case. Now assuming that all of them are online, let's say many of them are showing online but they are actually not online, right? They're showing online because of a present server trade-off, but actually they are not online. So they come back, they come to the system, they try to fetch the message together at the same time, they hit the same partition, and in case the partition becomes very hot, right, our worker system can actually save the partition in those kind of scenarios, right, for concurrent. So this worker system comes into action only for the read scenario, and especially for the offline use case or any use case where a lot of people come to read the message at the same time. Okay. And if the users are actually online, then our messages are anyway transmitted from one chat server to another chat server through the internal gRPC connections, right? It's just that it's not a single user, it's a group of user. So definitely, what I missed out here is that there has to be one, let's say that should I have this group service? I mean, this group service where the chat servers can actually ask that, hey, who are the followers or who are the members to whom I need to send this message? So this group service actually tells that, hey, this is the list of followers or this is the list of users. And then the chat server might ask the chat registry that for all these users which are the host, right? And then sends the message to all those hosts essentially for online use case, right? Or in fact, we might also do one thing that the group data can also be part of chat registry if it is actually feasible to do so. So in the same key value pair, I mean, in the same key value database, we have the group member details also. We have the chat registry data also, right? So we can write a service on top of this key value pair, key value database. So the chat server can just ask probably non API call that, hey, I have a group of people to send a message to. You give me all their connection. You give me all their hosts where they're connected. So in a single API, they can actually give this data to our chat server just to optimize it, right? And for online use case, it can actually transmit the message to all those concerned chat servers, like we discussed previously. Only for offline use case, or only for search use case, or only for use case where users are showing online, but actually they are not online, and they suddenly see a message, they want to hit the same partition. So that use case will be directly served by our worker system and our database cluster together. So there are two paths here total. Yeah. Is it clear or?
Yeah.
I think this offline use case will be always there, isn't it? Because I don't think so. We are very much optimizing the present server. There is some level of TTL there, and even if they are actually offline and they are showing online, that's actually perfectly fine because it's not a very critical use case. So it might happen that for a group, a lot of people are actually not online, but probably they are online 10 seconds back, right? So we try delivering the message. They are not able to get the message. Now they will come after some time, or they immediately comes again online, and it's now offline use case where they want to fetch the message. The client sends, "Hey, I retrieved previous message till this ID or till this offset. Send me the new messages." There should be some API to serve that, and then our worker system and Cassandra cluster works together to actually keep the data back to our to these users, right? Now, whether that data will come through some API or that data will be coming through again this WebSocket, that we can decide. That I'm not sure of right now. I mean, for offline message serving, we can hit API and get the message, or we might ask the chat servers in the WebSocket connection itself, and they might send us the data, right? Fetching it from the worker system and the DB cluster. So that's something we can decide later on. Yeah. Okay. So yeah, so this is something which is actually solving both online and offline use cases. Now there are a few other things that we did not scale. The chat registry. No, I think the chat registry that will be small, but still we need to have some level of backup there. So I think if we are going to use some key value store, let's say Redis, we are going to use here. I'll probably go ahead with the leader follower kind of system, the leader follower kind of topology, so that we have high availability there, and we don't lose out all the data there. So just to be clear here, in our system, chat registry is there in a single region only. So every time any chat server wants to talk to our chat registry, the connection will be probably across the ocean or across different regions. We need to see how it scales, but given that it's a very small call, right? And we might also do some level of optimization here, actually. The chat servers, right? I mean, one of the optimization might be the chat server has in-memory cache of their, of the chat registry of users with some TTL, so that it doesn't need to fetch the chat registry data from the key value pair from other region all the time. It can have in-memory cache with some TTL, which is essentially replicating or duplicating the same data, but it saves the time. In the worst case, what will happen? The message won't get delivered, right? But that's not probably very critical, because once the user actually comes back, or we are unable to deliver the message, next time the user logs into the system, it will anyway get the message, right? But we should be very careful about deciding the TTL there, so that we don't end up actually storing the stale data. But that's not optimization. I mean, I would still say not to do these kind of premature optimizations unless and until actually needed. But yeah, I'll probably go ahead with a leader follower kind of mechanism in chat registry to see how it functions. And depending on the performance, we can actually decide whether to go ahead with other level of caching or not. And for the present server also, this present server is nothing but again a key value store, which stores online, offline data with some TTL. So probably this present server, I mean, it might end up having data for all the 1 billion users or 2 billion monthly active users, right? So I'm assuming that at least on a daily basis, we'll have 50% of the users active. So on a daily basis, we'll have 1 billion users active. So we need to see what data, what spaces it actually takes to store this information. This looks like a very small information, right? Some user ID, some online offline information, and some detailed information, along with the database's own internal metadata. So if a single machine serves, then again, I'd probably like to go ahead with a leader follower kind of mechanism here to ensure high availability. If not, we might need to see if we need another level of partitioning here for present server also, right? Yeah, you have anything to add here?
No, I think that makes sense.
So a lot of things that we need to do are actually depending on scale and after basically doing load testing or after doing some level of study and estimation on the actual users, right? And see actually how it works and then make the decision to go ahead with some alternative system. But I'm just stating alternatives so that we know what are the different options available. Okay, so one more thing, I think did we talk about clients? You said that there will be multiple clients, multi-device support. So I'm assuming that by multi-device support, you mean that user A can be connected to mobile or user A can be connected to, let's say its own, desktop computer also. Let's say this one, right? Let's say it is connected through some desktop app also. So this is user A, desktop. So eventually what matters is that, okay, I mean, the same user can be connected to our chat system, but through different devices. So only a single user ID is not enough to identify the user. We need to have the device ID also and maybe device type also. I mean, something which makes it unique, right? So maybe device ID and user, a combination of them can identify different devices. Yeah. So it still might happen that both devices are not in sync. I mean, one device gets a message and another device probably doesn't get a message at the same time, but maybe with a delay of maybe 50 millisecond or 100 millisecond or something like that. Because we are not syncing the devices here directly from device to device like actually WhatsApp does. Rather, we are syncing the devices with the backend system. So, like the mobile, this desktop is also connected with this chat server only through a WebSocket connection that we discussed before. And now what happens is that we know that this user so in the chat registry, only the user information is not enough. We need to have user and we need to have device device ID. And let's take device type also. I'm not sure if we need this type for notification or any other kind of mechanism. But let's say that these three things together decide the client. Okay. So a tuple of these three things actually decide what is the client and where it is actually connected. So now our present server also have basically this this information. So instead of user, we'll have this essentially. Yeah. Okay. So what happens is that now let's say user B sends a message to user A, and user A is actually connected to two different machines. So now chat server NA should ask the chat server in Europe that, hey, for this particular user, what are the different clients connected? So it might happen that, okay, let's do it a little bit better way. So we might want to have, say, let's say this user to actually connected to a list of clients, right? To a list of client ID. So basically we'll have okay, we'll have user to client client one, client client two, right? And our client one is client. Client one is nothing but having some having the same user and having some device ID, right? Dev ID one, and having device type, let's say mobile, and these will actually have just you know, client one and client two. So this is not to replicate the exact data structure. The exact data structure might be different, but for understanding here, so we just keep a record of our users to their client, the map we keep, and we also keep which client is connected to which host and which region. So most likely, since it is the same user, they'll be eventually connected to the same host, right? So explicitly, this is what we are actually going to do, that whenever client, say chat server NA wants to send a message to you, it asks the chat registry that, hey, I have a destination user for it. What are the clients? Or give me the host and region. So this chat registry just checks what are the clients. And for all the clients, it actually gives the, you know, user device ID, sorry, it gives the host and region information to the chat server NA. And chat server NA just sends a message to all those hosts, essentially. Right? So this is kind of just to explain the whole thing, right? So there might be some level of optimization that since it is the same user, so eventually they're in the same region, right? So probably we might not need to fetch by client. We just simply fetch by user and send the message somehow, right? That also works, but that's up to our subject to experiment anyway. So yeah, so I think in this way we can actually handle these multiple devices also. Yeah. Any questions here you have?
No, I think looks good.
Okay. So are there any functional or any non-functional requirement that we have missed out here? So we've talked about message permanent storage. We have talked about multi-device support. We have talked about global app, boost chat use case. We have talked about the presence server. Yeah. Uh, yeah. Message ordering we have talked about with the Snowflake ID and eventual consistency. Yeah. Anyway, it's going to be uh, kind of eventually consistent only. We haven't talked about encryption and security, but do you know of any algorithm that WhatsApp or any client actually uses, any app uses to encrypt the data?
I mean, we can use any algorithm actually. As AES,
Yeah,
AES is two-way. Yeah, any
yeah,
algorithm is good.
I see. Yeah, I mean, anyway, we'll have encrypted WhatsApp connection, uh, right? And on top of that, we want to encrypt the messages also. So whether it's AES 256 bits or whatever is actually whatever suits our need, we can actually use that. Just that our chat servers should be able to transmit that encrypted data, right? And our client should be able to decrypt the data. So that decryption won't happen anywhere in between the system. And our message storage is also going to store encrypted data only or binary bytes only as a, you know, for the messages. Right. Okay. So yeah, I think we're pretty much there. Just that maybe in terms of deployment, our as we spoke of earlier, that our chat servers are, even though they are managing internal connections, right? But they don't store any state of the user's data, more or less anyway, right? So, I mean, probably technically you can call them as a you know, stateless, even though they're actually managing internal connections to other systems. But from a user perspective, they are stateless. So we can actually spin up multiple number of chat servers or application servers, and that should be perfectly fine as long as they register themselves to all other chat servers, or if we use PubSub, they register themselves to the PubSub system. Our chat registry spoke of our leader follower kind of mechanism. In a similar way, present server also leader follower kind of mechanism we spoke of, so that should be fine. Yeah, and our worker systems is also stateless. So if if the current workers actually doze off due to some memory issue or something happened inside, that should be fine. Maybe our read request will be terminated immediately, but new workers will actually take the up. And our Cassandra cluster is automatic system, with its own fault tolerant mechanism. So if we need to add more servers, we might need to do that manually, and we might need to trigger some repartition if at all required for if at all required, basically, if we foresee that circumstances. And in terms of monitoring, I think we can have monitoring on our DB API level, that what is the performance of the DB API in terms of latency, and what is the 95% or 99% latency of our DB APIs. In a similar way, we can have monitoring on our presence server, also on our chat registry also, right, on their APIs. And definitely in terms of hot partition measurement, we need to have some way to understand if Cassandra doesn't show it, right, or if there is no tool to actually show it, if any partition is actually getting hot or getting more number of reads or writes than other partitions, or after some threshold or beyond some threshold, it is actually getting read requests or write requests, then we'll be able to predict whether this partition is actually going to be hot partition soon or not, and what to do in time with manual human intervention, whether to scale it or repartition or something like that, right? And in our chat servers, we can actually manage, we can actually monitor the number of connections that are there. So if the number of connections in a specific region goes beyond certain limit, we can scale that. We can scale the chat servers in that region. Yeah, and yeah, this is pretty much. If you want to add anything, I can add, or do you have any other thoughts?
I think looks good.
Okay, if nothing else to add, I'll then stop the recording.
Yeah.
Okay, so we'll be waiting for our viewers to give us any suggestions or feedback on this. So viewers, let us know how you like, how you like this session, and what can be some of the topics that you want to see on this channel. We'll be waiting for your response. Yeah. So bye bye. Have a nice weekend.